let's discuss about recurrence relations. So in this session I am going to teach you how to write a recurrence relation for a recursive problem. So in algorithms, recursive problems are essential and very frequent. So whenever you have a recursive problem, to analyze it we need a recurrence relation. So recurrence relation is a formula which tries to represent a bigger problem into smaller problems. I will tell you what is that bigger problem, smaller problem concept. Example, I have an apple. I want to eat it. Okay. So let me represent it as a problem. I have a problem which is nothing but eating an apple, and the size of the apple, let's say n grams. Okay. So n grams. Now I want to eat this apple. Let me represent it as P of n. So P is nothing but eating problem and n is nothing but input size. That means apple size here. Now what I do is I solve this problem by dividing it into two parts and exactly half and half, so that it will be n by 2 grams, n by 2 grams. Now somehow I eat this part, somehow I eat this part. Okay. So initially my problem was eating this apple. If I denote it by P, if I use same technique and if I eat this apple, then that means I am solving a problem called P of n by 2. Isn't it? Eating an apple is P of n, eating n by 2 size apple is P of n by 2. In the same way, I eat this apple with same method, then that problem will become P of n by 2, isn't it? So finally, if you see, eating a big apple is P of n is nothing but solving a problem P of n by 2 followed by solving another problem called P of n by 2, isn't it? So eat full apple equal to eat half apple followed by eat remaining apple. So here you can see some sort of recurrence relation. So recurrence relation is exactly this kind of thing where we represent a recurrence term of n with some other recurrence terms of same style. Okay. So you see P of n is represented with P of n by 2 and P of n by 2. So that is the structure of recurrence relation. Okay, we'll see some recurrence relations for some of the problems. Let me explain some problems and after that I derive recurrence relations. In this session I am going to teach you how to write a recurrence relation for a problem. Okay, so that's it, but we don't solve them. To solve recurrence relations I will take one more session. In this session clearly we just write recurrence relations for given problems and you will be learning how to write a recurrence relation for a problem. Let's try. Yeah, let's start. The first question is how many binary sequences possible of size n? Okay, so the question is binary sequences of size n. How to solve it? Now I use clearly recurrence relations. Okay, that's what my goal. Any binary sequence can be imagined with n positions, isn't it? Let me draw that n positions. Position 1, position 2, position 3, so on, position n. Now let me do some work. My total work is filling all these n positions, isn't it? To form a binary sequence. For that definitely I have to fill the first position. How many ways I can fill the first position? Either 0, one way, second one, 1, isn't it? Okay. After filling 0, there is some other work pending, isn't it? We know that. Just remember it. So, if you fill 1, still something you should do. That means some other work is pending. You know what is that, right? Example, the remaining work is nothing but filling this n minus 1 positions, right? I don't know how many different ways you can fill this n minus 1 positions. Let's denote it by x. Now if you fill 1 here, the remaining problem is same, right? Filling this n minus 1 positions. So let me denote it by x ways. So try to understand. Finally, total number of forming binary sequences is nothing but filling 0 followed by finish the work, fill 1 followed by finish the work. If you can fill that n minus 1 positions with x ways, then total number of ways are x plus x, isn't it? Fill 0 and finish, fill 1 and finish it. So the number of ways are x and x, that's why 2x, right? But x is a variable, we have to find out x. Before that, let me introduce recurrence relation for it, recurrence term, T of n. Let me denote T of n for number of binary sequences of length n, remember it. Number of binary sequences of length n is T of n. Number of binary sequences of length 4 is T of 4. Number of binary sequences of length k is T of k. Now if you see this problem, the total number of binary sequences of length n, which is T of n, which we have to compute, equal to fill 0 and fill this n minus 1 positions. Then how many different ways you can fill this n minus 1 positions? T of n minus 1. That is nothing but x. Similarly, if I fill first position with 1, then remaining positions can be filled with again T of n minus 1 ways. Since we know that number of ways we can fill any n minus 1 positions is T of n minus 1. So T of n is related with T of n minus 1 and T of n minus 1. So answer is T of n equal to T of n minus 1 plus T of n minus 1. That means 2 into T of n minus 1. Whenever you write recurrence relation, you need a termination condition. I will tell you for the reason for that. Example, you have an apple, you want to eat it. Then my technique is cut it into two parts, half and half, eat it. Then you ask me how to eat this apple. Then again I tell you same technique, cut it into two parts and eat it and eat it. Again you don't have clarity how to eat this 1/4 part, isn't it? Then you will ask me again, then I will tell you that cut it into two parts and eat it. Then whenever you come with apple, then I say cut it into two parts, right? Then if you follow my technique, always you will be busy cutting the apple, you never eat. The reason, you don't know how to eat it, right? In your method, always you have to divide the problem into two parts, but there is no technique to eat it. So that's why if you don't write base case, that means at least if you don't know how to eat a small apple, that means if you don't know how to eat a smallest apple also, then you can't solve this problem with this method, right? Because every time I say that cut it into two parts, you never eat it. So that's why at some point of time you should stop this process, and that means example, probably when the problem reaches to very small problem like 1 gram apple or something, then again don't cut it into two parts. If you do that, it's infinite loop. So stop at some point of time, wherever you are comfortable eating the apple, then you stop it, and such kind of small apples you eat it. For that you should know procedure to eat it. At the same way, here also it is an apple problem. Apple of size n is divided into apple of size n minus 1, apple of size n minus 1. So at least you should know solution for some small problem. For me, small problem is binary sequences of length 1. Okay, so I am comfortable with binary sequences of length 1. If there is only one position, I can write 0 or 1, isn't it? There are two ways. So that's why T of 1, number of binary sequence of length 1 is 2. Now finally, I got recurrence relation. Let me write it. So T of n equal to 2 into T of n minus 1, T of 1 equal to 2. So this is about writing recurrence relations. Okay, so I will teach you how to solve recurrence relations in further sessions, not in this session. Okay, remember it. Now one more problem. You have binary sequences of length n without consecutive zeros. So how many such sequences possible? So example, if I have two positions, then how many binary sequences you can form without consecutive zeros? One is 1 0, maybe 0 1. Third one is 1 1, isn't it? Don't write 0 0, correct? So it violates the condition. Now how many such sequences possible for length n? Okay, so let me solve this problem using recurrence relations. That means for that I pose a problem, otherwise I form a problem such a way that it contains some recurrence terms. Okay, that means I have to solve it recursively. So let me take n positions, same idea, 1 2 3 4 n. I try to fill first position. So either I can fill with 0, otherwise 1, isn't it? if I fill first position with 0, then second position cannot be 0, isn't it? Then let me write 1. If I write 0 and 1, then this position can be anything, right? 0 or 1. So I can say that this third position is not at all depending on these first two positions, right? You can write anything. You can write anything, anything, but no consecutive zeros, right? So this entire chunk of these positions is a separate problem. This chunk is not depending on 0 or 1, right? So this problem exactly like again how many binary sequences you can form with n minus 2 positions, correct? So we have to form a binary sequence with n minus 2 positions without consecutive zeros. If I fill first position with 1, then what about second position? It can be anything. So this remaining entire chunk is not at all depending on 1. So they are all independent n minus 1 positions, but only thing is that n minus 1 position should be filled in such a way that no consecutive zeros. Now I want to say that my problem is no consecutive zeros. This problem is no consecutive zeros problem. This problem is no consecutive zeros problem. Finally, I converted my problem to same problem but with reduced size, isn't it? Let's do that. Let me denote my problem as T of n. T of n is nothing but number of binary sequences of this kind. That means no consecutive zeros. Then what is T of 2? Number of binary sequences of length 2 without consecutive zeros. We know that T of 2 is 3, of course. Now we have to find out T of n. That means recurrence relation. So if you see the problem, the total number of total number of binary sequences of such condition is either all sequences of this pattern or all sequences of this pattern. Do we have any other pattern? No. So how many binary sequences possible with this pattern? Since already you filled 0, 1 here. So how many different ways you can fill binary numbers here? That many. We know that here we can fill in T of n minus 2 ways. Since it is a n minus 2 size problem with same terms and conditions. So if you have n positions, number of such binary sequences are T of n, then with same terms and conditions, if you have n minus 2 positions, they are T of n minus 2. So how many binary sequences possible with n minus 1 positions where no consecutive zeros? T of n minus 1. Now what I want to say is the total number of solutions equal to either this kind of patterns which are T of n minus 2. So that means T of n equal to T of n minus 2 plus either this kind of patterns T of n minus 1, and the base case is T of 2 which is 3. Of course, why T of 2 should be base case? You can try one more, but you remember you need two base cases. The reason, there are two recurrence terms. To terminate it, you need two recurrence terms. Let me take one more smaller problem, T of 1. So T of 1 equal to number of binary sequences of length 1 without consecutive zeros. That means only you have one position. Then you can fill either 0 or 1. So anything, either way is successful, right? So that's why 2. Now we have two recurrence smaller problems and we have a recurrence relation, isn't it? So this is called recurrence relation. That's it. So we have seen two problems and we have created recurrence relations for them, isn't it? Let's see one more problem. So Raju is a 5 years kid and his problem is he want to take that chocolate which is at nth step, and he has n steps in front of him. Now Raju has two characteristics. That means he can be in good mood, otherwise bad mood, remember it, but it's random. So either he can be in good mood or bad mood, depends on the circumstances, anything like nature, weather, sometimes depends on his friends, their parents, everything. So we don't know at any moment whether he is at good mood or bad mood. Such a kid Raju is. Now this Raju is going to cross this n steps and he want to take that chocolate. Then how many different ways he can reach that nth position? But conditions is when he is at good mood, he will jump to 2 steps. That means he will take 2 steps. Okay, now when he is in bad mood, so usually, like, when people are in bad mood, what they do, they they will be very serious and they don't jump and all, right? That's why he take only 1 step. Now, but whether he is in good mood or bad mood is completely random. Anything is possible at any time. So then how many different ways he can go from step number 1 to step number n is the problem. Finally, he has to reach that n steps. Okay, so let me denote this problem as T of n. So T of n is nothing but how many different ways Raju can cross the 10 steps. Okay, so how to solve this problem? Here our goal is again converting this problem to smaller problems. For that, we take the help of Raju. We'll ask Raju, what are the possibilities you have, like what you do generally. I take step number 1 or step number 2 in the first phase. Oh, then after that what you do, Raju? After that I cross these remaining steps. Okay, whatever, if I take the first step, then I finish the remaining steps. If I take directly jump to second position, then I finish the remaining steps. Then I asked him, Raju, how you finish the remaining steps? That I don't want to reveal. If I reveal everything, so what you do, this is your problem. I only give you hint, but I don't solve completely. That is what Raju said. So then I slowly realized that we have to solve our problems on our own. So how I solve, you see now. This hint is enough for me. If Raju takes step number 1, that is one possibility, then remaining problem for me is crossing that remaining n minus 1 steps. But how many different ways Raju can cross that n minus 1 steps? Terms and conditions are same. If there are n steps, then Raju can do that in T of n ways. If there are n minus 1 steps, then Raju can do the same thing in T of n minus 1 ways. That I remember. If in the first place Raju takes a jump, like if he is in good mood, then Raju takes a jump, then he will reach second position. Then how many other positions he has to move? N minus 2. Then how many different ways Raju can cross n minus 2 steps? Again it is unknown thing, but it is T of n minus 2 ways, right? Now let me connect these dots. This dot, this dot, this dot. So connecting the dots. How I connect the dots is, so Raju can do only 2 things. He will take the first step and finish, or take the second step and finish. If Raju takes first step, there are remaining steps T of n minus 1. If Raju takes directly to second step, then remaining ways are T of n minus 2. Then total number of ways are these ways plus these ways. Isn't it so? Yes. So now we got recurrence relation, right? So successfully we have written third recurrence relation, right? Again, when there are 2 recurrence terms, we need 2 base cases. I will tell you the reason why 2 base cases. Let's take only one base case, that is T of 1. Okay, if you have only one base case, then T of 1 equal to, let's say, how many ways Raju can cross one step if there is only one step and there is a chocolate here. Now only one way, isn't it? Directly jumping into that one way. What is T of 2? If there are 2 steps, how many ways he can come to second step? I write all the possibilities. One is step 1, step 2. That means always bad mode. Second one, directly to step number 2. These are the 2 possibilities. That's why T of 2 equal to 2. If you don't write this one, if you take only T of 1, then how you compute T of 2? Let's try. So T of 2 equal to, according to this recurrence relation, T of 1 plus T of 0. Since you don't know T of 0, you can't answer T of 2. But if you have T of 2, I can answer everything. How? I will show you. Example, let me show here. If you know T of 1 and T of 2, all other values can be computed. Example, T of 3 according to recurrence relation, let me substitute n value 3 equal to T of n minus 1, T of 2 plus T of n minus 2, n is 3, T of 1. Yes, we have T of 2 and T of 1, isn't it? So let's take them. T of 2 is 2 and T of 1 1, 2 plus 1 is 3. In that way we can compute T of 3. If you know T of 3, we can compute T of 4. The reason T of 4 equal to T of 3 plus T of 2. In that way any value we can compute. Let's see one more problem. It's a robo problem. This robo want to go from 0 0 to 3 3. Okay. So but there are some terms and conditions. The terms and conditions are robo can either go 1 unit right or 1 unit up. It never comes back and it never goes down. With these terms and conditions, how many different ways? Let's say robo can go from 0 0 to 3 3. We'll see. One example, this path. Right, right, right. Since we have 3 rights, I am taking all of that rights and 3 ups. Okay. So if I take that 3 rights and 3 ups, I am reaching the destination. That is one path. Okay, 1. Now let me try another way. Up, 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 right, right, right. That means, so right, 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 up, 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 right, right, right. 2 ways. Is there any other possibility? Lot of other possibilities. Go up, take right, again right, right, up, up. Let me decode it. That is up followed by 3 rights, isn't it? 2 ups. By observing this paths, you realize that to reach the destination, always we have to take 3 rights and 3 ups. But eventually, like it's not compulsory to take consecutively, isn't it? Without taking 3 rights and 3 ups, we never reach that point. So that's obvious, right? Think about it. If you don't feel like it's obvious, so stop the video here and think about it. Why this robo has to take 3 rights and 3 ups? Now let me generalize the problem. If you have x rights and y ups, then how many different ways robo can reach destination? Okay, again destination is at that opposite diagonal, right? So how many different ways robo can reach that point? So let me write a recurrence relation for it. Let me use 2 dimensions. The reason our problem has 2 dimensions, isn't it? One is right dimension, second one up dimension. The total number of ways of, let me say the total number of ways of, crossing the grid. Okay, crossing the grid is the question, right? Crossing the grid is T of x comma y, where there are x rows and y columns. So I don't know which is unknown. We have to solve it. How I solve is, again I ask robo to reach from this 0 0 to whatever the destination you have. How you do it? Then robo said like this: I take 1 unit right first. Then I asked, okay, then what you do? Then robo said, remaining thing is a secret. I do something and I reach it. Oh, then what is the other way, robo? Then robo said, I go up, then I complete the remaining thing. But robo is hiding some details. What is that? After taking right, what it is doing, it is not explaining us. And after taking up, what is the remaining thing it is doing? It's not explaining us, and it is telling that we have to do that. Okay, then how we answer this question, we'll see. This hint is enough. Let's say, thank you robo, it's enough. We are going to solve this problem, you see. So how I solve this problem is, if the total number of ways are, let's say t x comma y, okay, that contains 2 components. First one is if I take right, that means robo takes right. If robo takes right, after that the remaining thing is it has to complete the remaining rights, right? How many other rights we have? X minus 1 rights. Okay, now how many ups still to be crossed? Same, right? Y. So the remaining problem is still x minus 1 rows and y columns to be crossed. Then how many different ways robo can do that? Robo said it's secret, but we know that if x rows and y columns can be crossed in T of x comma y ways, same robo with same terms and conditions, it can cross that appropriate rows and columns in T of x minus 1 comma y ways, isn't it? Now second, if it takes up first, then remaining work is filling the, remaining thing is crossing the other things, like how many other things are there? So other things are y minus 1 ups, isn't it? Because 1 up is gone, y minus 1 ups we have to, our robo has to cross, and still x rights, x rights has to be crossed. What I want to say is, same robo with same terms and conditions can cross this y minus 1 ups and x rights in t of x comma y minus 1 ways, isn't it? So finally I got the answer, that is the total number of ways of crossing x rows and y ups equal to t of x minus 1 y. That means these are all ways where robo takes right first. If robo takes up first, then the remaining ways are t of x comma y minus 1. These are the ways, and there is no other way other than these two. Then we have to add the total number of ways, right? So these ways plus these ways. So this is the recurrence relations t of x comma y. Again, base case. What is the base case for this problem is, when one dimension is 0, that means there is nothing, okay, then we have to stop it. If there is no right, that means you have 0 rights, only ups. Example of such situation is, you have, let's say, let me take this one, you have 0 rights and some 10 ups, okay. In such grid, how many different ways your robo can reach the destination? When there is no right, always if there is a up, then it goes like this, up up up. There is only one way, right? The possibilities comes when there is right and up. If there is only up, there is only one way. If there is only one right, like only rights but no ups, still there is only one way. That I take as a termination condition. So what I want to say is, this is the recurrence relation. Now the termination condition is t of k some rows and ups, like k rows comma 0 ups, then it is 1. So I terminate here. The second termination condition, if I have 0 rows and some k ups, then still I stop it. K here means any number of ups, but 0 rows, 0 rights, then I stop it. So these two are the termination conditions, okay. Using that, probably I can solve this question, okay. So from now onwards, whenever you have a problem, and try to think recursively. If you can somehow think recursively, and if you can solve it recursively, then probably you just remember that we have recurrence relations to analyze such kind of problems. Example, this problem we thought recursively. After that, immediately we solve this problem using recurrence relations, isn't it? So that's why recursion and recurrence relations goes together. When you have recursive problems, probably, I'm saying probably, if you want, you can use recurrence relations to solve that kind of problems, okay.